This video is going to be finding the surface area of those three-dimensional shapes we've been creating by taking a function and rotating it around an axis. So in this case, I've got this function, generic function f of x, and I'm going to rotate it around the x-axis. So I already took the liberty of reflecting f of x around the x-axis, so I wouldn't spend that time here on the video. So now I'm just going to make it look three-dimensional. So what we're going to do is find the surface area of this shape. And when I mean surface area, I mean the area just around the sides, not the area of the top and bottom as well. And we're going to do like we've always done. We're going to use cylinders. And this time, our cylinders that we're going to draw, the height of the cylinders are actually going to conform right to the function itself. So this is a little bit different. All of our other cylinders have been a little bit more blocky, but this one is actually going to fit right to the function. Now you're probably thinking, and I hope you're thinking, wait a minute, isn't that going to create a cylinder that kind of looks like this? But remember, we're going to draw an infinite number of cylinders inside of this. So the height of each cylinder is going to be getting smaller and smaller and smaller. So as we draw more and more cylinders inside of this shape, because they're going to be so small, the side lengths or the heights of each cylinder is going to start to look like just a single line segment with no angle to it. So the height of the cylinder can be found because it is forming to the function itself. We know that that's the arc length of the function. So the height is the square root of 1 plus the derivative squared. The radius is the part that's going to be the tricky part, if you will. In this case, the radius happens to be the function itself, but that's not going to always be the case. So the radius is the one you're going to have to try to figure out. Okay, so if we look at, we're going to find the surface area of a solid of revolution. In other words, those shapes that are created when we rotate a function around an axis. Okay, to do that, we're going to integrate because we're going to have a bunch of them, a bunch of these cylinders added together. And if we go from A to B, we're going to take the surface area of that cylinder, which is 2 pi, times the radius, whatever that happens to be, times the height, which will be the surface area of the function, the arc length of the function, dx. Okay, so that's how we find the surface area of a solid of revolution. Let's do an example. So we've got this function here, 9 minus x squared, and we're bound also by x equals 0, y equals 0. So that's just another way of saying it's this parabola that's opening downward, and we're bound in this first quadrant. So that region was rotated about the y-axis, and it created this three-dimensional shape. Okay, now if I draw in my representative cylinder, my cylinder is going to conform to the edge of this curve. So I know that the height of the cylinder is going to be the arc length of the function. It's the radius that's going to be a little bit tricky. So in this case, we know that the height is the square root of 1 plus the derivative. I might as well just find the derivative because this is something that's straightforward. F of x is 9 minus x squared, so the derivative is negative 2x. So there's the height. The radius in this case is not the function value. We can't just say that it's 9 minus x squared because the radius is coming from the y-axis and not the x-axis. So in this case, the radius is just some x value. And that x value changes as we move up and down the y-axis. Okay, so now we know the radius in this case is x. In the case up above, the radius was the function itself. All right, so it's going to depend on which direction the function is being rotated. If we're rotating about the x-axis, we have f of x. If we rotate about the y-axis, we have x. All right, let's write this out. We're going to integrate this from 0 to 3 because that's where that region that was bounded is from 0 to 3. It's 2 pi times the radius, which is just x, times the height, which is the square root of 1 plus 4x squared. Okay, I'm going to pull the pi out of here. Got 2x, square root 1 plus 4x squared. This one, we don't have a bunch of foiling that we have to worry about. I can see that the inner function, u, is 1 plus 4x squared. Du is 8x. So if I just make du 1/4 du, then that will be the 2x that we need. So if we rewrite this, we end up with 1/4 u to the 1/2 du. If I pull the 1/4 out, 1/4 pi. Now I can find the antiderivative. Add 1 to that, that's 3/2, so that's 2/3. 2/3 times 1/4 is 2/12 or 1/6. So I have 1/6 pi times u to the 3/2, so it'll be 1 plus 4x squared to the 3/2. We'll evaluate that from 0 to 3. If I plug in 3 first, 3 squared is 9. 9 times 4 is 36. 36 plus 1 is 37. So we end up with 1/6 pi. This is the square root of 37 minus, now if I plug in 0, see this is an occasion where you actually have to plug in 0. 0 squared is 0 times 4 is 0 plus 1 is 1. So that's minus 1. And that's it. That's the answer. Oops, I forgot to cube this. It's the square root of 37 cubed. Sorry, my apologies. Because it's the 3/2